This is a video about acids, alkalis and the pH scale. If you're doing AQA GCSE Chemistry, then this is part of Unit 4, which is chemical changes. But even if you're not doing GCSE yet, or if you're doing a different exam board, hopefully this will be useful to you. In this video, we're going to define the key terms acids, bases and alkalis. We're going to describe what we mean by the pH scale, compare strong acids to weak acids, explain how an indicator can be used to assign substances numbers on the pH scale, and finally use those indicators to identify whether substances are acids or alkalis. The name acid comes from the Latin word for sour, so pretty much all of the sour tasting things you can think of, like lemon juice or vinegar, are examples of acids. Lots of acids are made when non-metal elements react with oxygen to make an oxide, and that oxide then dissolves in water. So you might have learned elsewhere in your science course about how acid rain is caused by sulfur dioxide, oxides of nitrogen and carbon dioxide dissolving in clouds. We define an acid as having a pH less than 7, and we'll talk a little bit later on about what that pH scale is and what that number actually means. Acids are substances that release something called a hydrogen ion when they dissolve in water, so the pH scale is actually a measure of how many of those hydrogen ions are released. We can make predictions about how acids are going to behave chemically, so two things that they do is that they corrode metals and they react with carbonates to release carbon dioxide. You might have heard alkalis described as the opposite of acids, but if we're being really accurate, we should probably say that bases are the opposite of acids. So a base is any chemical that can neutralise an acid. That means stop it being acidic and move its pH nearer to 7, which is the neutral point. There are three main groups of bases that you need to know about, and alkalis are just one of them. The first two are metal oxides and metal carbonates. So if you take the name of literally any metal and put it in front of oxide or carbonate, we're talking about a base. So for instance, copper oxide or calcium carbonate. Those are examples of insoluble bases. That means that they don't dissolve in water, and that can be important because it can make it harder to give them a pH value. Later on in the GCSE, you'll do a required practical where you make a salt using an acid and an insoluble base. The third group of bases are the metal hydroxides, and we also call these the alkalis. They're called metal hydroxides because they're made up of some metal ions and some hydroxide ions. When an alkali, which is soluble, dissolves in water, it releases those hydroxide ions into solution. So just to be clear, because a lot of people seem to struggle with this point, all alkalis are bases, but not all bases are alkalis. Now we've already briefly mentioned the pH scale, but what on earth is it? Well, sometimes it's useful to know not just that a substance is an acid, but how acidic is it? How easy would it be to neutralise? And so for that we want to be able to write down a number, and that number is the pH scale. Now this is a measure of acidity and it's calculated based on the concentration of hydrogen ions, hence the capital H in pH. Remember, we said a minute ago that an acid is a substance that releases hydrogen ions when it dissolves in water. Slightly confusingly, a lower number on the pH scale tells you that there are more hydrogen ions, and this is to do with how it's calculated mathematically, but you don't need to worry about that until you get to A levels. The vast majority of substances in the world have pHs between 0 and 14, so those are the numbers that we use for GCSE. 7 is the neutral point, where something isn't an acid and it isn't an alkali. If a substance has a pH of less than 7, then it's an acid, and if it's more than 7, then it's an alkali. Here's an opportunity to pause the video and just double check that you're comfortable using the pH scale. Are each of these substances an acid, an alkali, or neutral? Hopefully that wasn't too challenging for you. pH 1 is an acid, pH 9 is an alkali, 4 is an acid, 7 is neutral, 3 is an acid, 8 is an alkali, and 0 is an acid too. The trickiest thing to understand about the pH scale at GCSE is that it's an exponential scale. So it's not the case that if you double the pH, you double the number of hydrogen ions, or you halve the number of hydrogen ions. The way the system works is that for each 1 that you go down the pH scale, the number of hydrogen ions increases by a factor of 10. So if we compare pH 1 to pH 2, pH 1 has 10 times more hydrogen ions. And if we compare pH 1 to pH 3, pH 1 has 100 times more hydrogen ions because you've increased by 10 times going down from 3 to 2 and then 10 times again going down from 2 to 1. The way to work this out mathematically is to figure out what the difference in pH is and then use this as a power of 10. If the numbers are going up, then you've got that many times less hydrogen ions, and if they're going down, you've got that many times more. Here's an example. Let's say I want to compare pH 5 to pH 10. 5 to 10 is an increase of 5. That means that the difference in the number of hydrogen ions is going to be 10 to the power of 5. So 10 times 10 times 10 times 10 times 10, which is 100,000. Because the pH is increasing, that means there are going to be fewer hydrogen ions. Here are 7 more questions of the same type for you to have a go at. Remember, for each one you need to think about the difference in pH and which direction it's in, and use that difference as a power for 10. This is good practice for your math skills. Okay, so for this first question, pH 1 is 6 points lower than pH 7 on the pH scale. So that means that our change is going to be 10 to the 6, and because it's getting lower, we're expecting there to be more hydrogen ions. So there will be 1 million times more hydrogen ions. pH 9 is 2 points higher on the pH scale than pH 7. So we're going to have 10 to the 2, 10 squared, which is 100, and because the pH is increasing, it will be 100 times fewer hydrogen ions. Using the same method, we can see that pH 4 will have 10 to the 3 times more hydrogen ions, pH 12 will have 10 to the 5 times fewer, pH 3 will have 10 to the 4 times more, pH 8 will have 10 to the 1, so just 10 times fewer, and finally pH 0 would be 10 to the 7 or 10 million times more hydrogen ions. Now that you understand the pH scale, we can discuss the difference between strong and weak acids. We said at the start that acids are acidic because when they dissolve in water they release hydrogen ions, but the truth is that not all acid behaves exactly the same when it dissolves. When substances dissolve, depending on their chemistry and the strength of their bonds, some of them remain intact, but some of them break apart into pieces, and if those pieces are charged we call them ions. So this process of separation can be called ionization or sometimes dissociation. So if we look at our strong acids like hydrochloric acid, sulfuric acid, nitric acid and some others you won't meet until after GCSE, when they dissolve in water they immediately completely dissociate or ionize. They break apart and release their hydrogen ions. So in this picture here, the little white circles are hydrogen, and when that acid dissolves, the hydrogen ions are immediately released, and this will make the solution acidic. If I compare that to a weak acid, like citric acid, carbonic acid, or ethanoic acid, then these acids are far less likely to dissociate and give up their hydrogen ions. I could have 1,000 carbonic acids dissolved in the same amount of water, and maybe only one of them would release its hydrogen ion. And that means that those weak acids are going to have far less of an impact on pH. I could dissolve quite a lot of citric acid in water and I still wouldn't see a very, very low pH. So if we compare them side by side, strong acids have a lower number on the pH scale than a weak acid that has the same concentration. So for instance, 0.1 molar hydrochloric acid, which is a strong acid, has a pH of 1, whereas ethanoic acid of the same concentration has a pH which, if we round it, is nearer to 3. In everyday life, an indicator tells us what is about to happen. If a car puts its indicator on, then I know it's about to turn. In chemistry, indicators help us to know which chemical reactions might happen. Here, I've got some hydrochloric acid, and I know that if I add a little bit of calcium carbonate to it, I'm going to see bubbles. It fizzes and releases carbon dioxide, and I can predict that that will happen because I know that it's an acid. But what if I didn't know that this liquid was an acid? I can use a chemical indicator to tell me that it is, and that allows me to predict that this reaction would happen. Different indicators turn different colours when they encounter acids, alkalis and neutral solutions. Two of the most common indicators you're likely to encounter at GCSE are litmus paper and universal indicator. Litmus paper can be blue or red. If I take this blue litmus paper and add it to some sodium hydroxide with a pH of 14, then I don't see a colour change. If I put it in some hydrochloric acid that has a pH of 1, then it turns red. And if I put it in this neutral solution with a pH of 7, then I also don't really see a colour change. If I try the same thing with some universal indicator paper, it turns blue in the alkali, a very pale yellowy green in the neutral solution, and red in the acid. The universal indicator is also available as a solution, so I can just add a little bit to each of these as well. And there I can see those same colours, blue in an alkali, green in a neutral solution, and red in an acid. Now that I know that these are the colours I'm looking for, I can test lots of other things to see whether they are acids or alkalis. One of the things that makes universal indicator so useful is that it's actually a mixture of different compounds that change colour at different points on the pH scale. And so that means it doesn't just have 2 colours or 3 colours, it can actually turn all of the colours in the rainbow. And that allows us to pin down more neatly exactly what the pH of a substance is. We can't just tell if it's an acid or an alkali, we can also start to identify strong acids and weak acids. So now that I understand what the different colours of universal indicator mean, I can use it to test lots of different substances to figure out whether they're acids, alkalis or neutral. So here in my spotting tile, I've got some toothpaste, some fizzy water, some vinegar, some soap, and just for fun, some tap water, so we can find out whether the water in Bracknell really is pH 7. So to each one, I'm just going to add a very small amount of my universal indicator. So what you can see here, well, it's a little bit hard to see with the toothpaste, but if you look at the edges, you can see it's going slightly blue. Cleaning products are often slight alkalis. Now, it might come as a surprise to you to see that the fizzy water has also turned a colour that suggests that it's an acid. This is because the thing that makes the water fizzy is that it has carbon dioxide dissolved in it. And when carbon dioxide dissolves in water, it makes an acid called carbonic acid. The vinegar is also an example of a weak acid. It contains a carboxylic acid called ethanoic acid. The soap is slightly acidic, it's a weak acid. And then you've got my tap water last, which is actually a slightly bluey shade of green, suggesting that the water here is ever so slightly alkaline. You probably think that this is chemistry that you can only try out in school, but the truth is that you've probably got at least one indicator at home with you. You can make a really good indicator out of red cabbage, but probably the easiest one to get your hands on is a fruity tea bag. If you've got one of those strawberry or blackcurrant tea bags, the ones that smell really good but then don't really taste of a lot, that lots of people just kind of have hanging around in cupboards, this actually makes a pretty good indicator. So I've got some sodium hydroxide and some hydrochloric acid here, and also some tea that I've just brewed up. And you'll see we get a sort of greeny, browny, khaki, not very nice colour in the alkali and a pink in the acid. So I could now use my fruit tea to go and test other substances. Thank you for watching, and I hope you found this useful. Don't forget to like and subscribe for more videos coming soon.